Hi everybody, this video is going to talk about linear functions. Now, previously we've talked about functions. This is getting more specific. Now we're looking at a specific type of function. Okay, so linear functions look something like this. Okay, they match this form y equals mx plus b, which you're later going to learn is called the slope-intercept form. Okay, but I just want to give you some examples of what they look like as equations, and then some examples of other equations that are not linear and the things to be on the lookout for, really. Okay, so let's start with what linear equations look like. Okay, maybe it's something like y equals 2x plus 3, where if we're looking back to our format here, the m value would be 2 and the b value would be 3. Okay, maybe it's just y equals negative 4x. Okay, if I don't have a value after this that's adding or subtracting, we really just think of it as being a plus 0 at the end, and therefore it still matches that format. Okay, another example would be y equals x minus 5. Okay, these are all examples of linear equations, and yes, we can have fractions. Maybe we have y equals 1/2 x plus 3/4. That would still be linear even though we have the fractions in there, okay? The m value would be 1/2, the b value would be 3/4. Now, here's the tricky part. It doesn't necessarily have to start off in this format. Maybe I have something that looks like this. Maybe I have negative 3x plus y equal to 10. Now, it doesn't match that y equals mx plus b format, but I can do something here. If I were to try and solve for y right now, I would have to add 3x to both sides. So I would add 3x here and on the right side. And what I would get from that is y equals 3x plus 10. So now it does match that format. So you've got to be on the lookout for these ones. This is something called standard form that we see occasionally. So if you see one like that, solve for y and see if it matches your y equals mx plus b form. Now, here are some giveaways for things that are not linear functions. Anytime you see an exponent greater than 1, okay, like x squared, then it's not going to be linear anymore, okay? If I had x to the third power, x to the fourth power, anytime I start getting exponents involved, it's no longer linear. Okay, same goes with special symbols. If I have the square root of x, it's not a linear function anymore. It's going to be an absolute, or I'm sorry, not an absolute value, a square root function. Okay, but another example would be the absolute value. Maybe I do have the absolute value of x. It's no longer linear. So anytime you get weird symbols involved, anytime you get these bigger exponents involved, it's no longer linear. Another thing to be on the lookout for is if x is in the denominator of a fraction. If we have this, it's also not going to represent a linear function. Okay, so things to be on the lookout for. So that's what it looks like as an equation. Now, graphically, linear equations, the way I think of it is the word line is inside of linear, okay, meaning that the graphs are going to be straight lines, okay? So this would be an example of a linear function. Or maybe it's a straight line, but it's going down this way. Okay, we can have horizontal lines. Or maybe we're changing the steepness. Maybe it's a little steeper than the other ones. Okay, these are all examples of linear functions. Now, here's the catch. If you see a graph that is a line, a straight line, no curves, no points, nothing like that, you can say that it is a linear function. However, there is one exception. The only exception is if we have a vertical line. If I have a vertical line, it's not a linear function, and here's why. If we use the vertical line test, when I draw a vertical line through my graph, guess what? It touches and crosses an infinite number of points. It fails the vertical line test, so a vertical line isn't a function. So write that down. And if it's not a function at all, there's no way that it can be a more specific type of function, meaning linear function in this case. Okay, but other examples would be, you know, maybe there's a curve in my graph, or maybe it's just like a circle. Okay, that, again, that wouldn't even be a function. Or maybe it has a sharp point that it comes to. Okay, this one catches people off guard a lot because each side is a line. Okay, that's a line right there. This is a straight line over here. The problem is it comes to this point here, so it's not just like one straight line. We have two sections of straight lines, kind of. Okay. Now, as a table, there's a specific pattern that we need to find here. Okay, what we need to have is we need to have a constant change. Okay, constant meaning we're adding or subtracting the same number each time. So add or subtract the same number each time in the x and y values. So as a table, what we're doing is we're not trying to figure out what we do to x to get y. We're looking between our x values. So to get from 0 to 1, I increase by 1. Again, increase by 1, 1 again, 1 again. So I have a constant change of plus 1 for my x values. Then we go and check the y values. For y, I add 2, and so on. So each time I'm adding 2 to my y value. So this is what I mean by a constant change in the x and the y values. Now notice we're not adding the same number to x as we are to y. Those are different numbers, but what we're adding to x each time is the same. What we're adding to y each time is the same. So this would represent a linear function. Okay, let's look at another one. Okay, check the x's first. This time it looks like we're adding 2 each time. So we do have a constant change in x of plus 2. Now we just check y. So let's see, I have to add 6 each time here. So we have a constant change in our y values of plus 6. We have a constant change in x and y, so it's linear. So here are some examples of tables that do not represent linear functions. Now, if we look at the x values, we can see that, yes, there is a constant change in the x values of plus 1, but when we go and check our y values, it's not, because we have to subtract 1 the first time and the second time, but after this, then we add 1 and we add 1. So we go from subtracting 1 to adding 1. If we're changing what we're doing, then it's not constant anymore. So this is not linear. Okay, same with this one here. Yeah, we have a constant change in our x values of plus 1. But again, when we go to look at our y values, we go from adding 3 to adding 5, and then 7, and then 9. And I have a lot of people ask me, well, isn't there a pattern in how much we're adding? Isn't how much we're adding increasing by 2 every time? And yeah, that's true. There is a pattern here. And that's for a different type of function that we'll learn about later. But for right now, for linear functions, we have to be adding the same number each time, okay? And in this case, we're not. We're adding 3, then 5, then 7, then 9. This does not represent a constant change, okay? So again, this one would not be linear. So the last thing that I want to look at is, what if we just have a set of ordered pairs? Okay, well, remember, we can represent a set of ordered pairs as a graph, a mapping diagram, or table. There's lots of different ways we can look at it. In this case, I think it's easiest to take your set of ordered pairs, okay, and you can quickly turn those ordered pairs into a table. Okay, let's just reorganize our information here. And then we can check to see if we have a constant change in the x and constant change in the y. Okay, so we have a constant change of plus 1, in our x values, and we actually have the same constant change in our y values here. So this would be an example of a linear function. Okay, I hope this video helped you guys. If you have any questions, remember to ask. feel free to rewind and rewatch. Have a great day.